In this video, we will see how to do a classification tree from beginning to end. We will start by building a full tree, and then we will look at the methods that JMP utilizes in pruning the tree to avoid overfitting. So we'll start with the universal bank data set. That should be in your folders. And to open up a data set in JMP, we can either double click the Excel file, or we can go here and click on open and then find the path where you have saved that file. So I'm gonna just open this. JMP will ask you if the variables have been imported correctly, and this is where, let's say that we had 2 or 3 rows of headers, we could make the adjustments here on where the data starts. So data starts, this refers to the data starting on the Excel sheet, not on the JMP sheet. So because we have said data starts on row 2, JMP assumes that the first row in the dataset would have been headers, and that's what JMP has done automatically, move these 2 headers. And we can also end where data ends. So suppose you had some annotations in the beginning or the top of the file, we could do that. If the data ended at a certain column and there was commentary here and JMP was mistakenly getting those incorrect, we could specify when data ends and when data begins. We can also hide columns, and we can tell data dump when data ends. So there are a lot of options in importing the data, making sure that the data that is coming in the correct format. So, and then we click on import. So this is our data set. This is the data table where we have ID, age, experience, income, zip code, and this is the example from the textbook where the scenario is that this is a bank, universal bank, who has certain clients which have been depositors with the company or with the bank, and bank wants to convert them to take out personal loans. So personal loans is a variable of interest, and bank's objective is to identify what type of customers are the ones who accept a personal loan application, and then use the rules that it forms with this to then score new potential clients into whether they are likely to accept a personal application or not. So this is our objective function. Now, as you know here, these annotations next to these variables suggest the type of variables that have been imported in. The blue histogram type of thing shows that the variable coming in is a continuous variable. However, for us, loan is a categorical variable. It is 0, 1, and so is securities, but it won't matter for regression trees or classification trees. But definitely this is our outcome variable, and this we need to change it into a nominal variable. So what we have to do is we have to click on right click on this little histogram here, and then we can say that this is a nominal variable, and then now we have this red histogram. So this tells JMP that the variable of interest is a nominal variable. Now we can build a tree on the entire data set. We have 5,000 observations, but then the problem is that yes, our tree will do an excellent job classifying to the last cell every data point that we have, but we do not know how this will do in real life or unseen data. And we know that there is a trade-off between how many splits we have and how well the model does in predicting or classifying new data. So what we will do is we will be doing a stratification or partitioning of our data like we have done before into training and validation. Now in CARD, we will be building the model on training, then we'll prune the tree on validation. So we need a third set of data. We call that test data, which has to be kept aside, and we will run our model on the test data to see how well we did with that. Also notice that we have not many customers as accepting personal loan applications. So if we just did a randomized partition, then it is possible that our validation set may have hardly any person who had been a loan candidate, and then we cannot really test the accuracy of our model with that. So what we will do is a stratified random sampling. In R, we can use create data partition from the caret package and do it a couple of times to partition out our data in training and then validation and test. Here we can do it all in one step. So before we get into, let's examine what is the distribution of personal loan in our sample. And we can do that in JMP by going to Analyze and we click on distribution. We can look at all the other variables, but we're interested in personal loans. So I'm gonna click on personal loan as a Y column and click OK. So this tells us that we have only 9.6% of our customers as being accepting the personal loan or having an account with personal loan. So the majority does not have a personal loan. So we want to be mindful when we are partitioning our data that we do get some of these cases in our validation set. And that is done by doing a stratified random sampling. A stratified random sampling essentially is a sampling on a Y variable, making sure that it has a good distribution or same distribution in all sets. So we go to Analyze and Predictive Modeling, and here we click on Make Validation Column. And it will ask us what do we want to stratify on. We want to stratify on personal loan. Click OK. And then these are the options about what percent do we want as training, validation, and test. We say that we want 50% of our data as training. We want 20 or 30% as validation, and we'll set aside 20% for test. So we have all our observations then split up into each of either of these three sets. And to reproduce our results, we will just set a random seed. Let's do this time 8976. Again, the only advantage of our use of seed is that we can then have repeated or reproducible results when we redo this partitioning again. Click Go. So now we have a column that's created as validation, training, and test. We can see that we will have the same distribution of people accepting loan in each of these sets. And again, another useful function in Tableau that we will use quite a bit is tabulate function. We can also do tables here. We can do pivot tables, but we will look at tabulate. We want to tabulate our personal loan application, so we can drop this here and we get the count. We can also add column percentage. So we have 90% of our applicants as not accepting personal loan and only 9.6%. But let's see how we did when we broke down our data into training, validation, and test. So we can move the validation column as our column, and we can just drag and drop variables in JMP when it highlights. So this means that it will now create columns based on the various observations we have in validation. So if we do this, we see that JMP has actually maintained this ratio in all these three sets. If we want to see count, we can throw count in as well. And then here we get the count and we get the percentage. So yes, this is a stratified random sample that we were able to create through JMP. Now first, let's try to build a tree and see what pitfalls that tree might have. So if we go to Analyze, Predictive Modeling, we go to Partition, and we will ignore our validation column. Let's just build the whole tree. So we will include all these variables except for zip code and personal loan as our X factors. So we can either drag and drop here, or we could simply click X factors and they get moved here. And then personal loan is our Y response. We click OK. And again, this is the beginning of our tree where we really do not have any partitioned classes. And our R square is 0. To build the tree, we'll click on Split. And then if you look at this candidate, this is what we were talking about as log worth or G-score. JMP will split first based on the variable which has the highest log worth. In the candidate models, income seems to be having the highest log worth. So if when we do the split, this is the variable that will get split. And then how will the value be chosen? Again, this will be chosen based on something that will minimize the impurities in the data set. So if we click on split, we have income cutoff as 99. So, and then we can also look at our number of cases. If we go to partition, click on display option, we can say show split probability and split count. So we click on split count, we see probability anyways. So here the first split that happened was income less than 99, and most of them were not personal loan applicants. In fact, 99% were not personal loan applicants, and only one was a loan applicant. I want to make one more change here. Let's actually prune this, go back to this, then prune. Let's not build any tree. We just are starting out with our basic default. I want to change one more setting. I'm going to click on partition and then click on minimum split size. The default size is 5. Let's change that to 1. So now we can keep splitting to a very granular level if we have that option. So this tells us the minimum number of fractional proportions that gets split. So if we click on split, income was 99, and now between these two, which one will get split first? Let's examine the candidates. So here, the log word that seems to be high is for credit card average, that's 65. Let's see what is here. Here we have a pretty high log word for a bunch of variables. The one that stands out is education. Now notice that here we have a pretty clean group, so this is not a candidate for the next split anyways. This is where we have still an impure classification because we have 35% of observations who accepted loan applicants and then 65 who didn't. So when we were to click on split, split will happen on this branch or on this node, and it will happen on education, and we can verify that by clicking on split. So I'm gonna just minimize this again and click split. So we see that the split did happen here. It did happen based on education. And what level of education? Well, those who had bachelor's, because it was high school, bachelor's, and post-bachelor's. We can keep doing this analysis, and let's again just for one more time look at the candidates. We see candidates among these, income as being highlighted as having log worth of 111 and the G squared value of 335. And then again, notice here, this is where the cut point will be. So JMP has looked at each of these predictors, looked at the various points at which they can be cut, and then looked at the candidate. So there's a lot of calculations going in the background, even in just getting this table out. And we can see here, we have a bigger option than family, and then 349, and log worth is 93. So between these two, the log worth of income is 111, and that's higher than this. So we can expect the split to happen on this node and at income with a cut point of 118, and that's what we can verify when we click split again. So we click split, and this is indeed what happens here. At 118 is the cut point, and at each branch now we can keep clicking on split. And notice as we click on split, let's focus on R square. Now we have had 4 splits now, and we have R square of 7.75. We keep increasing the split, and R square is increasing, and we're just growing the tree as much as we can. And look, the tree is getting really convoluted and rather large. We've already had 15 splits. R square keeps going up, split. And if I keep doing this over and over again, I will eventually get a really big tree with R square close to 1. And this tree gets very, very unwieldy and hard to comprehend and then develop rules. Even though it is doing a perfect classification of our entire data set. If you want to look at the rules that have been able to get derived from the tree, we can go to the partition, and let's look at the leaf report. We have had these 25 rules here, and again, as I said, we can keep going, but these rules become impractical, and even though they are doing a perfect job of fitting our training set, they are overfitting our real data, and they will do poorly when we have real data. We can also look at the fit report here. show fit details, and because we haven't really split our column, it has been able to achieve a misclassification rate of only 0.0096. So we have very close to a perfect classification. We have some error here and we have some error here, but as we keep doing the split, we will get rid of these. However, this is a classic example of overfitting the data, and when we were to do this on new data, we will not be able to replicate these results, and thus this overtly rosy model will be a poor indicator of how well our model will do with new data.